In this presentation, we're going to look at digital to analog converters. We're going to take what we know about combinations of resistors, series and parallel combinations, and use that to convert a binary input into an analog output. You may recall when we introduced binary numbers that we took some physical thing like a voltage, maybe a voltage with a range between 0 and 5 volts, and we wanted to work just in binary. We wanted everything to be high, close to the 5, or low, close to the 0. And that's the way things are going to be on the inside of the computer. But we also want to have output, that the computer can output something into the analog world. And so we'd like to be able to somehow convert binary inputs, things that are close to 5 volts and close to 0 volts in this scenario we're talking about right now, and get more intermediate values. Can I get 2.5 a voltage? So can I recover intermediate values in my range for a pseudo-analog representation of numbers, or quasi-analog as I say here. So the purpose of a digital to analog converter is to get information, data that is inside the computer and thus in binary, which is just a special form of digital, and get it to the outside world, which is analog. Think about your computer running a speaker or putting an image on a monitor and so on. We need this binary digital information to be converted to analog to interact with humans in the world who live in an analog world. So you recall when we played with binary numbers, we introduced the concept of binary fractions. So there was a bit representing the halves place, another bit representing the quarters place, and so on, so that we could make fractions. So we're going to get these intermediate values by thinking of the digital input as a binary fraction, and then we want the voltage that corresponds to that fraction. So if our binary input corresponds to a half, we want to get half the voltage. If our range is up to 5 volts, we would like to get 2.5. There we would have a representation of a quarter. If we put in a quarter, we want to get out a quarter of our maximum voltage. So we would like 5/4 of the voltage in that case, and so on. So here we just remind you of fractions, and so we have fractions in decimal, where 3.14159. After the point, the numbers of 10 are negative powers of 10. So the first digit, the 1, is the tenths place, the 4 is in the hundredths place, the next one is in the thousandths place, and so on. We have negative powers of 10. So when we move over to binary and we are after the dot again, then we have negative powers of 2 this time. So that first number after the dot is the halves place, 2 to the minus 1. The next 0 is in the quarters place. That third digit after the dot is the eighths place, and so on. So let's remember then our highs and lows are corresponding to something physical, typically a voltage. So our high and low are a high voltage and a low voltage based on some range. Let's just take as an example 5 volts. So our highs are something close to 5 volts, our lows are something close to 0 volts. And a voltage is sort of an energy per charge. So let's go over to the resistor side of our thought process here. You leave a battery, you have some voltage, you have some amount of energy, and you're going to travel a circuit to get back to the other side of the battery, and you're going to move, let's say, through some resistances, and you're going to use up all of your energy in the total path, but you're going to lose up part of your energy as you move through each part of the circuit. And so if we stop and measure the voltage somewhere along the way, it will be an intermediate voltage. We're not measuring as we leave the battery where it's 5. We're not measuring just before it returns to the battery where it's 0. But we're measuring the voltage somewhere along the way in the circuit, and thus we're picking up an intermediate voltage. So we can see that in this example of resistors in series. We are leaving, in this case, a 10-volt battery. We're going through a 2 kilo ohm resistor followed by a 1 kilo ohm resistor. They are in series. Any current that went through the 2 must go through the 1. And then we look at the voltage across the 1 kilo ohm resistor and the total resistance was 3. If we did an equivalent resistance of 2 and 1 in series, we would add them and get 3. But the voltage across just the 1 kilo ohm resistor is then 1/3. We need 1/3 of our energy for this, and so it is 3.31. So we're getting a partial 10 in this case is our high, 0 is our low, but we're getting some intermediate value based on the values of our resistors that were in this case in series. In order for us to achieve the digital to analog converter, we're also going to need the concept of parallel. So here we show the first kilo ohm resistor is in series with a parallel combination. So the two lower resistors are in parallel. There's a connection of wire on the top, a connection of wire on the bottom. That's our definition of parallel. Resistors in parallel add reciprocally and end up with a smaller overall resistance. And so then that parallel combination has a smaller resistance and then thus requires less of the energy. So more of the energy is used in the top 1 kilo ohm than in this parallel combination at the bottom. Our simplest version of a digital to analog converter is going to be a voltage divider. We're going to have two resistors in series. So part of the voltage will be dropped across one, the rest will be dropped across the other. So then if we take the voltage at the point between the resistors, it is going to be some fraction of the overall voltage. So somewhere between the high and the low, an intermediate value. So the circuit here can be called a voltage divider. It can also be called a 1-bit digital to analog converter. We have a 5-volt battery, so we're considering 5 volts to be high and 0 volts to be low. When we connect the switch, which is a digital input, so we're inputting a voltage of 5, a binary digital high input, and then that voltage goes through two resistors of equal value, so that the voltage halfway through is half. And so we've put in a 1, and we're thinking of that 1 as a binary fraction, a 1-bit binary fraction, and a 1 in the halves place, then we would want half of the voltage as an output, and that's what we have. The other possible 1-bit fraction is, of course, 0 in the halves place, which would be 0. So if we flip the switch down to low, then we are directly connected to the ground on both sides of the circuit. So we're putting in a low, so there's just no voltage going in the circuit whatsoever, and we get a 0 out. So previously we put in a high representing the halves place, and so we got half of our voltage, and now we are putting in a low, and we get nothing, we get a low. So we've achieved what we wanted. We have a fraction, which is either a 1-bit fraction, which is either half or 0. So now we want to go beyond just a 1-bit digital to analog converter, and so we want to add additional inputs, more switches, and we want to be able to achieve other fractions. So if we add 1 bit, that would be a 4ths place, and we should be able to achieve 3/4, 1/2, 1/4, and 0. And then if we added a 3rd input, that would be an 1/8 place. And so if we put in 0.101, that would represent 1 in the halves place, 0 in the quarters place, and 1 in the 1/8 place. So we would be looking for 5/8 of our maximum voltage to be output in that case. Okay, what you are seeing here, I am claiming, is a 2-bit digital to analog converter. It has a 5-volt battery, so 5 is considered our high and 0 our low. We have two switches that are connected to either high or low, depending on which position the switch is in. So we have two binary inputs, A and B, I'm calling them. We have the the switch A is connected to what should look familiar. The two resistors coming down from A are what we had before in what we call the voltage divider, or the 1-bit digital to analog converter. And the switch B is connected to a 1/2 kilo ohm resistor, half as much resistance, and is attached to the middle between the two other resistors. Okay, so we're putting in this case, a low input, and so there is no voltage coming from switch A, and there's no voltage coming from switch B, and so then there is, of course, the reading is of 0 voltage. So that's easy to understand, but it's one of the 4 states we need. We are looking for, if we put in low, low to get a 0. If we put in low, high, we are looking to have 1/4. If we are putting in 1/0, we're looking to have a half. And if we're putting in 1/1, we're looking for 3/4. So I have to convince you of 4 different states, and now I've convinced you so far of 1. So the next state I will tackle is 1, 0, where B is the 1. So B is the halves place now, and A is the quarters place. So B is high and A is low. So we're going to come out of the top of the battery. We're going to go through B. We see that half a kilo ohm resistor, and then we come from there, and then we see the 2 1 kilo ohm resistors, and they are actually in parallel. So I'm going to sort of show you on the next slide. So, but they have a wire connection coming between them, and that's one wire connection. And then there's a wire connection on the other side that loops through the switch down and next to the ground. So those 2 1 kilo ohm resistors, they may be tricking you and trying to tell you that they're in series, but they are, with the way that we are connected right now, they are in parallel. And now let's look at them in parallel and finish the analysis. So for the input of 1, 0, which was switch B high and switch A low, the 2 1 kilo ohm resistors were in parallel. 2 1 kilo ohm resistors in parallel, adding reciprocally as resistors in parallel do, result in a half a kilo ohm. So in order to go from the high end of the battery to the low end of the battery, we first pass through that half kilo ohm that was connected to switch B, and then we connect to these 2 in parallel, whose equivalent is also a half kilo ohm. So at that halfway mark there, we are indeed at halfway. We are using up half the voltage for the first part and half the voltage for the second part, and the dividing voltage is 2.5, half of our maximum voltage. So now we're going to look at state 0, 1, where B, the halves place, is low or 0, and A, the quarters place, is 1 or high. So we leave the battery and we go through switch A, and then we go through the top 1 kilo ohm resistor. Then at that point, at node X, the current will split. Some of it will go over to a node Y, up through the half a kilo ohm resistor, through switch B, and down to node Z, and then to the battery. The other part of the current, again at node X, will go down through the lower 1 kilo ohm resistor, and then to node Z, and finally to the lower end of the battery. So the lower 1 kilo ohm resistor and the half kilo ohm resistor are in parallel. There's a connection of wire on one side. Node X and node Y are just connected by a wire, so that's a wire connection. Then there's a connection on the other side of the resistors. So on the other side of the 5 kilo ohm, there is a wire that goes through switch B and then down to node Z. And on the lower end of the 1 kilo ohm resistor, the lower 1 kilo ohm resistor, there is a direct wire connection to Z. There's a wire connection on one side, XY, and there's a wire connection on the other side. Both of them connect ultimately to Z. And so they are in parallel. So let's look at that. So first we go through switch A and through the upper 1 kilo ohm resistor, and then we had the half kilo ohm and the 1 kilo ohm resistors in parallel, and the equivalent resistance is a third. So I go through a 1 and then the equivalent of a third. So altogether I have to go through 4/3. By the time I reach that middle junction, after I've gone through the 1 kilo ohm, I've used up 3/4 of my energy, and I have 1/4 of my energy left. So I have, of my 5 volts, I have 1/4 of my 5 volts, or 1.25 voltage left. So I've achieved the fraction of a quarter. The final state I need to account for is the high state, which should be 3/4. So B, the halves place, is high, and A, the quarters place, is high. So I come out of the battery and I go through both switch A and switch B, and the current that goes through A is going through the upper 1 kilo ohm resistor, and the current that went through B is going through the half kilo ohm resistor. And those two currents are combining at junction X and then going through the lower 1 kilo ohm resistor. So the upper 1 kilo ohm resistor and the half kilo ohm resistor are in parallel. There's a wire connection. See, the XY nodes are the one side of connection, and then the upper sides of those two resistors both connect to the junction I labeled W over there just above the battery. So they are a parallel combination. So let's look at that. So this is almost the previous scenario flipped on its head. After coming out of the 5-volt battery, I encounter a parallel combination of the 1 kilo ohm and the half kilo ohm in parallel. So that gives me a equivalent resistance of 1/3 of a kilo ohm. And then I must go through a 1 kilo ohm resistor, and then I am home and done. So at the time I've gone through the parallel combination and reached the sort of middle junction, then I have used up 1/4 of my energy, and I have 3/4 of my energy remaining. So the voltage you see there is 3/4 of my 5-volt maximum. And so I have achieved my final state where 1 is giving me 3/4 of my voltage.